Hi Matt, how's it going?
Hi Edgar, how are you doing?
Oh, pretty good. I've got this handy laser and I need to expand the beam and collimate it at the same time. Do you have any idea of how to do this?
Well, it's funny you should ask. We have something like that set up right here.
Whoa!
I know, right? Here we have a beam expander to expand and collimate the size of our beam, and we have a system set up to profile the output of that beam.
Nice.
Pretty amazing, huh? Alright, here we have our setup of our beam expanders. We have two lenses separated by the sum of their focal lengths. With this beam, the beam expander is an afocal system, so it'll take an input beam and turn it into a larger output beam, where the magnification is the ratio of the two focal lengths. In this lab, we use this beam expander to create the larger beam that will allow us to have a smaller beam waist later in our system than we would be able to get without the beam expander.
So for the first part, in order to create our beam expander, we introduced a 0.25 numerical aperture microscope objective, and we aligned it to the laser as we have done in the previous two labs. However, once we introduce the microscope objective, we begin to also introduce imperfections into the beam and aberrations. So in order to control those, we introduced a 10 micron size pinhole that acts as a low pass filter so that it filters out the higher spatial frequencies introduced to the beam. We had 3 degrees of freedom, we had X, Y, and Z translation, and we moved these accordingly so that as our output we just got the airy disc pattern. As you can see, the pattern begins to appear, and once our concentric circles outside, which are caused by diffraction, are removed, we know that we have filtered. This is an illustration of how our input beam was filtered. We have our input beam that is imperfected going through our objective, which then transforms the beam into the frequency domain. You can clearly see the higher frequencies outside of the airy disc. This then passes through a pinhole that is placed a focal length away so that all light is passing through, and acts as a low pass filter that results in a clean profile of our beam.
Okay, once we got the spatial filter in place, we wanted to create something called the Keplerian telescope. Now, the Keplerian telescope would take in a small beam and output a large beam. Now, to do this, we had two focal lengths, f1 and f2. We separated the two focal lengths by the sum of their focal lengths to create this telescope. But how do we know that we have a collimated beam on the output? We used a shear plate to test for this. While the distances may not be perfect, if they are, we'll see these straight line fringes associated with this reference mark on the shear plate. If you look closely, you can see the ray fan diagram, and you can see a cubic tendency. This implies that there's a small amount of spherical aberration inside of the system. If I move the lens, you can see that the fringes are not orientated with the reference mark. So this is how the shear plate works. It basically makes an interference pattern on an image screen. So you've got the input beam right here. The first beam reflects off the first surface, and then another beam reflects off this second interface. The two beams are incident and create this interference pattern. If they're plane waves coming in, a collimated beam, you'll have fringes that are aligned with the reference mark on top of the shear plate. If the beam is divergent, you'll have them orientated at a positive angle from the reference line, and if they're, a negative angle away from the reference line, they're convergent.
So after setting up our Keplerian telescope and collimating our beam, we introduced a 200mm focal length lens to image the laser beam waist. We then introduced a knife edge as previously done in the lab, and we took measurements to profile our beam before the focal point, at the focal point, and after the focal point. And this is the data that we obtained.